So, hello everybody, and welcome to the session Bridging AWS Accounts through Shadow Resources. In this session, we will demonstrate you how we found several vulnerabilities in AWS. The most severe of this vulnerability could allow an attacker to inject an admin role to another account. So, let's start by discussing the most debatable topic on AWS, which is AWS Account ID. So each account has a unique identifier associated with it. This identifier consists of 12 digits, and the most important things about this identifier is that some treat it as a secret, and the other don't. And along the history of AWS, we have many different opinions whether it's a secret or not. Although AWS in their official documentation state that this identifier should be shared carefully, they do not consider this as a secret. But we, as security practitioners, know that attacker could achieve problematic things only by knowing this account ID. So, what is the right answer? Are AWS account IDs secret or not? We hope that by the end of this session, we will all have more solid opinion about this. So, let me introduce ourselves. My name is Yakir, and here with me is Ofek Itach. We are security researchers from AWS Security Team Nautilus, and we would like also to thank Michael Kaczynski, who contributed to this research. So let's start by discussing how our journey began. Well, we worked with the AWS Management Console, which is the GUI of AWS, and specifically with the CloudFormation service. We noticed that when a user uploads a template file, AWS, behind the scenes, creates an S3 bucket for the user. Although the user did not explicitly ask AWS to do so, this is how the service behaves by default. We have decided to name this kind of resources that are generated automatically shadow resources. So now let's define this term. Shadow resources are resources that are generated automatically or semi-automatically by AWS. Most of the time, they are spawned without user intervention, and they might go unnoticed by the account owner. And the great example of shadow resource is just the S3 bucket that we saw that AWS creates for the CloudFormation service. And I want us to align some basic knowledge about S3 bucket, which is one of the first services by AWS. This service has some special uniqueness. For example, S3 bucket name must be globally unique across AWS. So, for example, if you create an S3 bucket under your account that's called cool bucket 1, no one else on AWS can create a bucket with the same name. So let's set up a gear and talk about our first vulnerability in CloudFormation. So first of all, what is CloudFormation? It is an infrastructure as code service by AWS, similar to the Terraform project. A user will define a template file that contains several AWS resources. Then the user stores this file locally or in S3 bucket. And then the user will submit this template file. It's called create stacks. So different resources under this template file will be deployed under the account of this AWS user. And as I said before, when user using the CloudFormation service, CloudFormation creates an S3 bucket for the user behind the scenes. Now, I want us to focus on the naming pattern of this S3 bucket. It consists of three parts. First of all, a prefix, which is a constant value, in this case, CF template. Then, an hash, which is a unique value per account. And then we have the region, which is related to where the user initiates the CloudFormation service. So, whenever the user uses the CloudFormation whenever the user uses the CloudFormation service via the GUI, the CloudFormation service creates an S3 bucket for the user with this pattern. And then, when the user uses the CloudFormation again in a new region for the first time, AWS, behind the scenes, creates a new bucket with the same prefix, with the same hash, but with a different region. So the only difference between this bucket name will be in the difference part. The hash will be unique per account. So this bucket is a semi-predictable bucket. So what if an attacker creates this S3 bucket before the user? If an attacker does so, the attacker actually does something that's called S3 bucket name squatting or bucket sniping. You can read a great blog post about this technique by Owen McKay. Now I want us to visualize this technique. So we have the user that using the CloudFormation service on a specific region, and then we have the attacker that somehow leaked the hash of this specific user and creates this S3 bucket under the account of the attacker. So whenever the user will try to use the CloudFormation service for the first time in this specific region, the CloudFormation service will try to interact with the attacker S3 bucket, and it will fail. So we have here a way to prevent a specific user from using the CloudFormation service in a specific region, which can be considered as a DOS scenario. And a DOS scenario is fine, but it isn't enough for a security conference. So let's escalate it. So what if an attacker opens this bucket for a public access? The reason why the user got an error before is because the attacker still needs to define some settings on the S3 bucket. First of all, the attacker needs to allow public access to this S3 bucket because it's blocked by default. And then, in order to allow cross-account access, the attacker needs to define a resource-based policy in this S3 bucket. Here we have a very permissive S3 bucket policy that allows any principal on AWS to perform any action on this S3 bucket. So after the attacker does this, now the CloudFormation service will succeed to interact with the attacker S3 bucket. So whenever the user uploads a template file to the previously vulnerable CloudFormation service, this template file will be stored in the attacker S3 bucket. So the attacker can enumerate this file, find secret, resources, and more. So we have here an information disclosure scenario. But if the attacker already has access to this S3 bucket, what if an attacker modifies this template file? And if an attacker does so, the attacker actually does something that's called resource injection in CloudFormation template. You can read a great blog post about this technique by Rhinolab, and also credit to Mott Fuller about this technique. And all the idea behind this technique is some time of check, time of use issue that the CloudFormation service has by default that allows an attacker a window of opportunities to modify template file before the CloudFormation service deploys them. So the attacker can modify this template file manually or with a Lambda that will do it automatically. Now I want us to visualize this. So we have here the CloudFormation service and the attacker account. The attacker creates this predictable bucket name under their account and also a Lambda that will be triggered by an event that's called put bucket notification. So any file that will be dropped to the attacker S3 bucket, the Lambda will be triggered and inject malicious resource. So whenever the user will try to use the CloudFormation service via the management console and uploads a template file, this template file will be stored in the attacker S3 bucket, and the Lambda will be triggered. The Lambda will get the template file from this S3 bucket and perform a resource injection. In this case, the Lambda injects an admin role that can be assumed by the attacker. So now the Lambda puts this template file, this backdoor template file, to this S3 bucket. So after the user will try to deploy this template file and actually do something that's called submit stack, the previously vulnerable CloudFormation service will get the template file from the attacker S3 bucket and create the injected resource. So we have here an admin role on another account. Now let's see a quick POC. We can see that the user using the CloudFormation service and upload a template file. Behind the scenes, this template file is already dropped to the attacker S3 bucket, but the user still needs to define some settings on this CloudFormation service. Now we can see that the attacker gets this template file, so the attacker can backdoor it manually or with a Lambda. And if we will view the logs on the victim side, we can see that the victim has a new role, an attacker role, an attacker user. In this case, it's an admin role that is trusted by the attacker account. So all the attacker needs to do is to find the related account ID of this victim and assume this role. So now the attacker has an admin role on another account, which is one of the most severe things that we can achieve in the cloud.
But Yakir, before we continue, let's not ignore the elephant in the room. Previously, you told us that the bucket name needs to be predictable. But when we look at the bucket name, it's definitely not predictable, right? That is something that we need to figure out. And this is what we do. We started by enumerating every possible bucket. But we quickly realized it is just not doable because we have too many options. Then we thought to ourselves, maybe there is a way to reverse the hash. Because as Yakir showed you before, every time that we create a new bucket, we get the same ID over and over again. But we didn't succeed there either. Then we thought, maybe we go to open source. And in open source, we stumbled upon this code. And in this code, we saw that the bucket name and the hash in the bucket name is not a hash. It's actually a randomized string. And this is really bad for us. Because without the hash, our technique is worthless. So we had to rethink about everything. But as good security researchers, we managed to find solution to our problems. So we searched in open source, in GitHub and SourceGraph, and we managed to find over 1,000 hashes. So basically, we could attack thousands of organizations. And we didn't stop there. On top of that, in open source, we managed to find that some of the bucket names in AWS created with account ID in them. And the account ID is the unique identifier. And that was a eureka moment for us, because we understand that we can just leave the mysterious hash and focus on finding new bucket patterns with account ID in them. And that's exactly what we did. We started to try to find every possible bucket name in AWS by using open source like before, by using the AWS documentation and SDK. We started crawling and pressing nearly every possible bucket in AWS. And we created some automations. Eventually, we ended up with hundreds of buckets. And we need to understand what to do, because we need to understand which bucket is related to what service, and we need to understand if any of these buckets are exploitable. And this is what we discovered. We managed to find 5 more vulnerabilities in AWS. Some of them requires just the account ID. So every vulnerability is slightly different by the exploitation technique, but the vector is the same. So let's take a quick overview over all of them. In Glue, we managed to inject Python script and change them. That way we get remote code execution. In EMR, we managed to inject Jupyter notebooks. Using this, we managed to inject cells to the Jupyter notebook. And by doing that, we could basically inject XSS. And when the user uses the notebook for the next time, we will stall his credentials. In other services, we managed to find data manipulation and even those scenarios. All of them requires just the account ID. And you can see all of them in our blog. Now let's talk about open source projects. As you may know, many open source projects use S3 bucket behind the scenes. So here are a few examples of open source projects that are vulnerable to our technique. And this is because they doesn't verify the owner of the bucket, which means when they uses the project and if we predict the bucket name, they will drop the files into our account. Now, to prove that we can attack open source project, we just took one of the biggest open source projects related to AWS, which is CDK. It is a project by AWS to manage your cloud account. In CDK, we found out that the bucket name is predictable. and you already know the drill. If the bucket name is predictable, we can come to the picture and we can take over the bucket. We have only one condition in CDK. We need the user to delete the bucket after he bootstrap. Only then we can claim the bucket and inject code into his templates. And you are probably asking yourself, what is the probability for such thing to happen? So we checked it, and it is 10% of CDK users do that exact mistake. They deleting the bucket after they bootstrap it. Now, I'm proud to introduce you a new technique we named bucket monopoly. Bucket monopoly is pretty simple. In the previous example, we showed you that the bucket name, in the previous example, we showed you that we exploit one service in one region. In bucket monopoly, we will take all the regions. We also want to increase the likelihood of success for our attack. So instead of taking one vulnerability, let's try to use all of them. Now, we implemented as many services as we could. That way, whenever the user uses the service for the next time, he will be exploited. We talked with AWS about all of the vulnerabilities that we found, and they mitigated all of them, and AWS is no longer vulnerable to our technique. But many open source projects are still vulnerable. So we have a couple of recommendations to how to mitigate it. And our first approach is try to limit the role you are using in your project to only access resources in the wanted account. You can do that by IAM policy. We also recommend to use one of AWS supplied headers called expected bucket owner. That way you can guarantee that your project doesn't go to other buckets. And we recommend do not use predictable bucket names. Instead of using a bucket name like this, try to use a bucket name that has randomization in it. So, after everything that we showed you today, do you still believe AWS account ID isn't a secret? Thank you, everybody, and have a good day.